So, as promised, we are going to talk about linear regression briefly. We're actually going to spend an entire chapter talking about linear regression. So, this is really just a very slow introduction, a smattering of the ideas. But here I have an example, a real example actually. It's a scatter plot. So each blue diamond is a sample data value of ultrasound fetal weight estimation. So basically when an ultrasound tech estimates the weight of a fetus in the uterus while the baby is growing, and then the actual birth weight of the child. So once the baby is born, they measure it using a more accurate procedure. But the idea then is we have this scatter plot, and we have a good idea that there might be a linear correlation trend here. Now, I want to call your attention to this piece right here. So often when you encounter a scatter plot with a regression line, they're going to give you the R-squared value. And just to remind you, so what they call R-squared, right, is also known as the coefficient of determination. Its exact meaning we'll talk about later in this course, but what's important about it is that we get the coefficient of determination from the linear correlation coefficient. So, I mean, literally, R squared is R squared. Which means conversely, if you have the R squared value, you can find what R is, actually. One really important thing to note is that R squared is always positive, okay? So it's a positive statistic about the strength of correlation. It doesn't tell us the direction. Unless we have the scatter plot, then we know the direction of the correlation. And here we can see that it's positive because the trend line has a positive slope, okay? So then we could, calculate what R would have to be. So if you calculate the square root of 0.7646, 7646. One interesting thing to note, and you may remember this from algebra, that if your number that you're taking the square root of, if it's between 0 and 1, that means the square root is actually going to be greater. So it's counterintuitive. It's interesting, which means that R here is 0.874 roughly, okay? And we know it's positive again because we have positive linear correlation here. And this is evidence that, we have a strong linear correlation here, okay? So we're justified in setting the regression line. So what the regression line is, right? So it's a model. It's a mathematical model. Or actually, I should say statistical model. So the regression line has a form. Y hat equals AX plus B. This is an equation of a line, okay? And Y hat is the predicted Y value that corresponds to the X value that we pick. Okay, in other words, in the context of this example, let's say we're thinking about a new data value, okay? So an ultrasound just came through into the database, and we found an ultrasound weight of 3,500 grams. This is all in grams, right? So it's not in pounds. It's So based on that, we can use a regression line to predict what the actual birth weight would be. Specifically, it's a point on that line, right? And the actual birth weight, right, you can figure out from the line. So in other words, our 3,500 grams is our X value that we would substitute in. And if we had the equation of this particular regression line, then we could figure out what exactly we're looking at here. Does that make sense? Now, since we don't have the equation, then we can't do this precisely, okay? But in general, this predicted y value, if we have a data point somewhere in the sample that doesn't match that exactly, that happens. That's okay. In other words, the prediction might not always bear out, okay? But the regression line is like our best estimate, and we also call this the line of best fit, where in some way, which we'll discuss later, this is kind of the best approximation or the best prediction that we have for finding the y value for an x value for bivariate data, okay? And so regression lines are actually super powerful, okay? We use regression in a lot of different contexts. This is what is also sometimes called simple linear regression, because there are some simple assumptions that we take here. And as we'll see in a later chapter, there are more complicated forms of linear regression, including what we call multiple regression, which is when we have multiple variables, okay? So no longer are we talking about bivariate data, but we would be looking at multivariate data with 3 or 4 or 5 or 6, however many components, okay? But this is characteristic. This is the regression line template. And some things to note here, just a review in case you're, in case you're a little rusty on your algebra. Totally understand that. Happens to everyone, including myself. So B, right? B is what happens when your x value is 0. So we can call that the base rate or baseline response value. So what happens when x equals 0, right? So what happens when we don't have any, in other words, what if the ultrasound fetal weight is 0, right? Which it doesn't make sense in this context, but if it's 0, then what would B be? That's what we're talking about here. And A is the slope of this line. In other words, it is how fast does the y value change with respect to the x value. So we call that the rate of change in y with respect to x. It's a slope, right? So if A is positive, then we know that we have positive linear correlation, and if it's negative, then we have negative linear correlation.